A woman walks slowly through an upscale shopping district and stops in front of a green handbag. The surface feels soft, the color is uniform, the stitching is precise, and the bag holds its shape much like a conventional premium leather product. But what makes this bag interesting is not its appearance. It is where the material began, not with a cow, not entirely with conventional synthetic materials. Its original raw material came from a drought-resistant plant, the prickly pear cactus. The interesting part is not simply that a plant can be turned into a handbag. The real story is the entire industrial system behind it, how the cactus is cultivated, which parts are harvested, how moisture is removed, how the biomass is processed, how the material is formed into sheets, and how a relatively low-value agricultural raw material can eventually become a material suitable for fashion, interiors, and other high-value applications. If you are interested in understanding how new materials are actually made, rather than simply hearing marketing claims about green materials, stay with us until the end, because the most important part of this story is not the handbag. It is how dry and economically difficult land may become part of a much larger industrial supply chain. The prickly pear cactus, scientifically known as Opuntia ficus indica, has one obvious advantage. It is naturally adapted to dry conditions. Its thick pads store water. Its biological structure helps reduce moisture loss. And its root system can make use of limited water in the soil. From an engineering perspective, this matters. If an area cannot support crops that require large amounts of water, the conventional solution is often to build irrigation systems. But irrigation means pumps, pipes, energy, maintenance, and additional operating costs. And in many dry regions, water itself is already scarce. Prickly pear approaches the problem from the opposite direction. Instead of changing the environment to suit the crop, we select a crop that is already suited to the environment. That is one of the reasons this plant has attracted attention in dry regions of Mexico and in areas with similar conditions in India, China, and parts of Africa. When prickly pear is cultivated on an industrial scale, the field cannot simply be planted at random. The soil is prepared. Plant spacing is calculated. Rows are organized to make maintenance, harvesting, and transport easier. Access roads can be established between production areas, while collection points are placed as close as practical to the fields. From the air, it may look like little more than a cactus plantation. In reality, it functions much like an outdoor biological raw material factory. The inputs are land, sunlight, naturally available moisture, and planting material. The output is biomass that can be harvested repeatedly. And this is where another technical advantage becomes important. According to the production model we are following, when the goal is to harvest cactus pads for industrial raw material, the first usable harvest may begin in roughly 80 to 90 days after planting, depending on growing conditions and the required specification. When the objective is fruit production, the timeline is much longer. Around 3 years before the plantation reaches the fruit-producing stage described in this model. But the important point is that the field does not have to be replanted after every harvest. Once established, prickly pear behaves more like a perennial production asset. The mother plant remains in the ground. New pads continue to grow. Mature pads can be harvested, while younger growth is retained for future cycles. Instead of repeating the entire planting process every season, growers can focus increasingly on management, selective harvesting, and maintaining the plantation. This changes the economics of the crop. With many annual crops, each new season means another round of soil preparation, seed or seedlings, planting labor, and establishment costs. With prickly pear, much of that burden is concentrated in the initial establishment phase. Once the plants are successfully growing, the same plantation may continue to generate biomass over multiple cycles. Propagation is also comparatively straightforward. Rather than relying only on seeds or complicated nursery systems, healthy cactus pads or sections can be taken from established plants. The selected material is cut, cleaned, and disinfected to reduce the risk of disease. It is then placed under suitable conditions to develop roots and new growth. Once sufficiently established, the young plants can be moved into the field. For regions with limited capital, basic equipment, and lower levels of agricultural mechanization, this simplicity can become an important advantage. Workers move through the plantation and select mature pads. They cut them close to the base, but the entire plant is not removed. The main structure and younger shoots remain. The plant continues growing and produces more pads for later harvests. From a production point of view, this means one plant can continue generating biomass through repeated harvesting cycles instead of being destroyed after a single harvest. The freshly harvested pads are collected and loaded for transport. At this stage, however, they still contain a significant amount of water. Transporting fresh plant material over very long distances is inefficient because a large part of the transported weight is simply moisture. The factory does not need to transport that water. What it needs is the useful plant matter that will become part of the material production process. That is why primary processing near the growing region can be so important. At the pre-processing facility, the cactus pads are washed. Soil, dirt, spines, and unnecessary material are removed. The pads are then cut into smaller pieces, increasing the surface area and making the drying process more efficient. In regions with strong sunlight, the local climate itself becomes part of the manufacturing process. The cactus material can be dried naturally for several days, reducing its moisture content before further processing. From an engineering perspective, this is a logical step. Removing water near the source reduces transport weight, improves storage stability, and prepares the biomass for grinding. A region that was once considered disadvantaged because of intense sunlight can now use that same sunlight as part of the pre-processing system. Once sufficiently dry, the material is fed into grinding equipment. The purpose is not simply to produce a powder. The objective is to convert irregular plant material into a more uniform feedstock that can be handled and controlled more precisely in the next stages. Useful plant components are then processed. These may include fibers, proteins, and other fractions of the biomass that can contribute to the structure of the finished material. At this point, the problem is no longer primarily agricultural. It has become a materials engineering problem. An industrial material has to be repeatable. One production batch cannot be extremely soft, while the next is unexpectedly rigid. Thickness cannot vary randomly. Layer adhesion cannot depend on guesswork. If a material is going to enter industrial production, its characteristics have to be controlled. This is the boundary between a craft material and an industrial material. And this is also where one of the most common misunderstandings has to be corrected. Cactus powder does not simply turn into leather by being pressed together. To create a material that is soft enough to bend, strong enough to resist tearing, and stable enough to retain its surface, the plant-derived material has to be combined with other components. The formulation is adjusted for viscosity, flexibility, strength, elasticity, color, and its ability to bond to a suitable backing layer. The mixture can then be coated onto a substrate. Rollers control thickness. Layers are pressed, dried, stabilized, and inspected before the material moves into surface finishing. So, it is more accurate to think of cactus leather as an engineered composite material containing plant-derived components, not a cactus leaf being transformed directly into a sheet of leather. Once the base sheet has been formed, it still does not have the appearance or performance expected from a premium material. Additional processes may include rolling, pressing, embossing, coloring, adjusting gloss, adjusting softness, surface treatment, and mechanical testing. According to the supply chain model we are following, material that has been pre-processed in producing regions may then move to more advanced material processing centers. Italy is particularly relevant because of its long history in leather finishing, surface treatment, fashion materials, and high-end manufacturing. The value of the material is no longer measured by how many kilograms of cactus were harvested. It is measured by what the material can actually do. Is the surface consistent? Does one production batch match the next? Does the color remain stable? Does the material bend without cracking? Can it survive cutting and industrial sewing? Can it maintain its appearance after repeated use? These are the questions that determine whether a material can move from an agricultural experiment into a premium industrial supply chain. If you enjoy this kind of analysis, where we look beyond the finished product and examine the actual engineering behind it, subscribe to the channel. There are many materials that look simple on the surface, but hide extremely complex production systems underneath. A sheet of material that looks attractive in a showroom tells us very little about its actual quality. What matters is how it behaves after thousands of movements and repeated use. Manufacturers can test tensile strength, tear resistance, repeated folding, abrasion resistance, layer adhesion, color stability, and compatibility with industrial sewing. If the material is too soft, a handbag may lose its shape. If it is too stiff, cutting and sewing become more difficult. If the surface coating does not bond correctly, it may separate after repeated use. If the color is unstable, the finished product can lose its visual quality very quickly. This is why much of the value is not in the cactus itself. The value lies in the ability to control what happens to the material after the cactus leaves the field. Once the material passes the required tests, it can enter product manufacturing. Cutting machines create individual components: the body of the bag, the base, the handles, reinforcement pieces. The parts are sewn together, edges are finished, hardware is installed, stitching is inspected, the surface is checked. And finally, the same green handbag from the beginning of our story appears again. But now we can see the chain behind it. Plant, biomass, processed raw material, engineered compound, material sheet, surface finishing, finished product. So where does cactus-based material stand when compared with conventional animal leather and synthetic PU or PVC? High-quality animal leather still has major advantages. With proper care, it can last for many years or even decades. It can develop a distinctive patina over time. And it has a very long history in footwear, furniture, accessories, and luxury goods. PU and PVC have different advantages. They are generally easier to manufacture at scale, offer consistent appearance, and can be produced at lower cost. But many lower quality synthetic materials may trap more heat and can eventually crack, peel, or separate after prolonged use. Cactus-based materials are trying to occupy another position. Their raw material story begins with a plant. They can be relatively lightweight. Their surface can be engineered for consistency, and their characteristics can be modified for different applications. According to information presented for this category of material, some products are promoted as having useful service lives of several years, depending on construction and use. Some commercial descriptions also claim high levels of potentially biodegradable content, but those claims should not be accepted simply because the raw material comes from a plant. A serious evaluation has to examine the entire product system. What percentage of the final material is actually plant-derived? What is the backing layer made from? What binders and polymers are used? How much energy is required during processing? How long does the final product actually last? Can it be repaired, recycled, or biodegraded? And what happens to it at the end of its useful life? A plant-based origin does not automatically make a material environmentally superior. Its full life cycle matters. There is another reason prickly pear is interesting from an industrial perspective. A plant that produces only one commercial output is usually less efficient than a plant that can feed several value chains. The pads can become a source of biomass for material production. The fruit can enter an entirely different processing line. It can be sorted, washed, crushed, or pressed, filtered, processed, and bottled as juice, or used as an ingredient in other food products, and the remaining biomass does not necessarily have to become waste immediately. Depending on composition, safety requirements, and local processing methods, some residual material may be investigated or used for livestock feed, compost, organic fertilizer, or other applications. This changes the economics. Instead of asking, what single product can this plant produce? The more useful question becomes, how much of the plant can be turned into value before we finally call the remainder waste? That is the basic logic of a more circular production system. And at the same time, in poorer and more remote regions, the story can begin very differently. Not with a large industrial plantation, not with hundreds of hectares, but with small farms, family plots, and communities living on land with limited water and poor soil fertility. In favorable agricultural areas, farmers have many choices. They can grow grains, vegetables, fruit trees, and many other commercial crops. But as water becomes scarcer, soil becomes less productive, access to machinery decreases, and available investment capital falls, the number of realistic choices becomes much smaller. This is where a drought-tolerant perennial crop becomes economically interesting. If a crop requires sophisticated irrigation, heavy fertilizer use, expensive equipment, and large upfront investment, the poorest farmers are often excluded before production even begins. Prickly pear may offer a lower barrier to entry. Initial investment can be comparatively limited. Propagation can be simple. Water demand can be lower than many conventional crops. The plant can tolerate poorer growing conditions, and, once successfully established, it does not have to be replanted after every harvest. For low-income regions, that combination can be important. Imagine a household in a dry part of Africa. The family has a small area of land. Water is limited. Available capital is low. If they choose a crop that requires regular irrigation, the cost of pumps, water storage, energy, and irrigation equipment may already make the project unrealistic. A drought-tolerant plant, such as prickly pear, may allow production to begin at a smaller scale. A few rows can be planted. Propagation material can be taken from established plants. The plantation can then expand gradually. Mature pads can be harvested and sold to a local collection or pre-processing center. Fruit can be sold separately or sent for processing. Residual biomass may have additional local uses. One plant begins to create several possible streams of economic value. And this is where the idea becomes more important than simply producing an environmentally friendly handbag. A cactus standing alone in a field does not eliminate poverty. A crop does not create prosperity simply because it survives in dry soil. Poverty reduction comes from a functioning economic system around the crop. There must be buyers. There must be collection centers. There must be quality standards. There must be basic pre-processing capacity. There must be transport. There must be reliable market demand. And most importantly, enough of the final value must remain in the producing region to make continued cultivation worthwhile. If farmers grow cactus but no one buys it, the system fails. If processors purchase only when prices collapse, farmers have no reason to maintain the crop. If every high-value stage takes place thousands of kilometers away, while the producing community sells only very cheap raw biomass, the economic impact on the growing region will remain limited. A stronger model, therefore, tries to keep more activity close to the source. Local collection, local drying, local grinding, local jobs, basic technical training, farmer cooperatives or purchasing networks, clear quality specifications, predictable demand. When those elements exist, land that once had few profitable agricultural uses may become a raw material production zone. A household with few income options may gain another source of revenue. And at sufficient scale, such a system may help reduce economic vulnerability in regions exposed to drought climate instability, and limited agricultural opportunity. This is why dry regions of Mexico, India, China, and Africa are important to watch. Mexico has a long cultural and agricultural history with prickly pear. India has vast semi-arid areas. China has regions facing water stress and desertification. And across Africa, many communities live in environments where irregular rainfall makes conventional agriculture extremely difficult. Prickly pear will not automatically transform those regions. But when appropriate growing conditions are combined with processing infrastructure and real market demand, the plant can become another productive option. And the entire chain does not need to exist inside one country. One region may specialize in cultivation. Another may perform primary processing. A separate factory may produce an intermediate material. A high-technology processing center may carry out advanced finishing. And global brands may design, assemble, and sell the final product in completely different markets. This kind of distributed supply chain is already common in modern industry. What makes the cactus story interesting is that it creates the possibility for dry, low-productivity land to become one of the first links in a high-value international production system, not by competing directly with fertile agricultural regions, but by exploiting an advantage those regions do not necessarily have: the ability to produce useful biomass under harsh, water-limited conditions. Now return once more to the green handbag. In the store, the customer sees only the final object. Behind it, however, may be a much longer system. Someone prepares the land. Someone establishes the plants. Someone manages the field. Someone harvests the pads. Someone dries the biomass. Someone grinds it. Someone formulates the material. A laboratory tests its mechanical properties. A finishing plant creates the required surface. A designer specifies the final product. A worker cuts and sews it. A logistics network moves it across countries. A retailer displays it, and only then does the customer pick it up. This video has changed the way you look at a simple consumer product. Tell us in the comments, do you believe plant-based materials, such as cactus leather, can become a serious long-term competitor to conventional leather, or will they remain a specialized alternative? There is one final technical question that matters more than any marketing slogan. Is this actually better for the environment? The answer cannot be determined simply by seeing the words plant-based. We need to know the real composition, the percentage of plant-derived material, the backing material, the polymers and binders, the energy required for processing, the transportation distance, the useful service life, the possibility of repair, the possibility of recycling, and what happens after disposal if a material reduces fossil-derived content but fails much sooner than the material it replaces. The total environmental benefit may be smaller than expected. This is why serious material evaluation requires life cycle thinking rather than a single attractive claim. The woman leaves the shopping district carrying the green handbag. She may never know where the cactus was grown. She may never know who harvested it. She may never see the sunlight that dried the biomass. She may never know how many times the material was rolled, pressed, coated, tested, colored, and inspected. She may never know that the same plant can also produce fruit, food ingredients, beverages, organic residues, and potentially other useful products. And she may never know that somewhere else in the world, a family living on dry and nutritionally poor land may be searching for exactly this type of crop, one that needs relatively little water, one that can be propagated simply, one that can begin producing harvestable pads in a comparatively short period, one that does not have to be replanted every season. But that is precisely why this story matters. Dry land is not necessarily worthless land. A plant that survives in a desert is not necessarily just a symbol of hardship, and a low-value agricultural material does not necessarily have to remain low-value forever. When agriculture, processing, materials engineering, manufacturing, and markets are connected correctly, prickly pear can move from a dry field to a pre-processing facility, from a pre-processing facility to an engineered material, from that material to a high-value product, and potentially from that high-value product back into economic opportunity for the region where the raw material first grew. Prickly pear is not a miracle crop. It cannot eliminate poverty by itself. It cannot replace every traditional material, and it does not automatically become sustainable simply because it comes from a plant. But it demonstrates a powerful industrial principle. When the right crop is matched with the right environment, the right processing technology, and the right market, a simple biological advantage can become the foundation of an entire value chain. And perhaps that is the most important part of this story. Not that a cactus can be turned into leather-like material, but that something growing on dry, difficult land can be transformed into a product that belongs in a completely different economic world. If you want more documentaries where we break down industrial processes, new materials, manufacturing systems, and the technology hidden behind everyday products, subscribe to the channel and turn on notifications, because in the next video, we will continue asking the question that matters most. Not how modern a product looks, but how it is actually made, and whether the value behind it is truly sustainable.